In this video, we'll talk about how to find position vector of a particle moving along a straight line between 2 points with a constant acceleration when its initial speed and position are given. So let's start. So we have this particle at the point P0 whose coordinates are 1, -1 and 2 at the time t equal to 0, and its speed is also given at the time t equal to 0, and the speed is equal to 2, and it's moving from this point towards the point B whose coordinates are 3, 0, 3, and it's moving along the straight line AB with a constant acceleration given by 2I plus j plus k, and we want to find its position vector at any given time r. So first let's understand the relationship between acceleration and position vector. Acceleration is given by second derivative of the position vector with respect to the time t. So if we integrate acceleration of this particle with respect to time twice, we can find its position vector. So we'll also find two constants of integration during this process, but then we need to find values of these two constants. So let's see how to do that. So acceleration is given to be 2I plus j plus k, and this is our equation number 1. So we integrate it with respect to time and we get velocity of the particle equal to 2I plus j plus k into t plus constant of integration c1 vector. Now we see that this velocity is a function of time, and when we substitute t equal to 0 here, what do we get? That velocity at the time t equal to 0 is equal to the constant of integration c1. Okay, so we know the value of c1. If we can find velocity of the particle at time t equal to 0, we know the constant of integration c1. Okay, now integrate this equation, let's call it 2, with respect to time again, and that gives us the position vector rt of the particle, and this is equal to 2I plus j plus k into t square divided by 2 plus c1 into t plus c2 vector, which is another constant of integration. Now if we substitute t equal to 0 in this expression for the position vector, we see that this constant of integration c2 vector is nothing but the position of the particle at the time t equal to 0, which we already know how to find because we are given that at time t equal to 0, the particle is at the point P0 whose coordinates are 1, -1 and 2. So therefore the position of the particle at time t equal to 0, which is equal to the constant of integration c2, is nothing but the position vector for the initial point P0, which is I minus j plus 2k. So we know the value of the constant of integration c2. So the only thing left to do is to find the constant of integration c1. So c1 is equal to velocity of the particle at time t equal to 0. So now what is the expression for the velocity vector? V is equal to magnitude of the velocity vector multiplied with the direction. What is the direction? Direction is same as the direction of the vector AB, because the particle is moving along the straight line AB. So the direction for the velocity vector is that of the unit tangent vector along the line AB. So therefore t vector is nothing but the unit tangent vector along the line AB. So the equation for this unit tangent vector would be AB vector divided by magnitude of AB vector. Now what are the direction ratios for the straight line AB? Now that would be 2, 1 and 1. So therefore the unit tangent vector along the line AB would be 2 times I plus j plus k divided by magnitude of AB vector, which is square root of 6, and therefore the velocity at the point at the time t equal to 0 is given by magnitude of velocity, which is equal to speed, and speed is given to be 2 multiplied with this unit tangent vector, 2I plus j plus k divided by square root of 6, and that gives us a value of our constant of integration c1 2. So now we know the value of both the constants c1 and c2. We substitute them back in the expression for the position vector r of t for the particle, and we have our answer.